Last video, we learned how to predict a number. And while numbers are useful, what happens if the thing we want to predict isn't a number? What if we want an answer? Yes or no? Malignant or benign? That's a completely different kind of problem. And it turns out the way a computer learns to answer it is surprisingly beautiful. This is classification, and in this video is where things get interesting. So to help motivate this idea, let's meet our dataset. Each row here is a tumor cell, and for each cell we know certain things, certain features. For example, the radius, how large the tumor is, the texture, how irregular surfaces appear, the smoothness, how rough its boundary looks. Dozens of measurements all taken from a single cell. And at the end, one label, malignant or benign. Now, here's what I want you to do. Don't think like a computer yet. Think like a doctor. Look at these numbers. What would push you towards malignant? A bigger radius? A rougher texture? You probably have some kind of intuition already. And that intuition is exactly where we're going to start. So here's one way of answering the question. How do we make a prediction? Well, we've seen this before, linear regression. We take each feature, we multiply it by some weight, and we add them up. And that result comes out to be a number, a score you can think of. Higher score, more likely malignant. Lower score, more likely benign. Seems like a solid approach, so let's try it. And we get 1.7. Okay, what does that mean? Is 1.7 malignant? Is it benign? We don't know, because nothing in our problem lives at 1.7. Let's try another cell. Negative 63. Or this one, 12,000. These numbers aren't wrong exactly, they're just uninterpretable. We asked a yes or no question and we've got a number that lives nowhere near yes or no. So we don't need a better line per se. We need a completely different kind of output. Something that stays between 0 and 1, something that helps us make the decision, and that's exactly what we're going to build. So we need a new kind of output, not a raw score, but more so a probability. And probabilities have certain rules. For once, they can't be negative, and they can't be greater than 1. So whatever you choose to build, its output must stay between 0 and 1. But there's another requirement. Remember the score from before? A larger score means the cell looked more suspicious, more likely to be malignant. A smaller score meant the opposite. That information is valuable. We don't want to throw it away. So larger scores should move us closer to 1, and smaller scores should move us closer to 0. And one last thing, we're eventually going to train this model, which means making tiny adjustments again and again. To do that, our function should be smooth. No sudden jumps, no sharp corners, just a gentle curve. So it should be, now let's see our candidates. Take a moment, which one would you eliminate first? This one looks promising, it stays between 0 and 1, and bigger scores, they will produce bigger outputs. But zooming near 0, something strange happens. The curve suddenly changes direction. The function exists, but the derivative doesn't. Not ideal. And now we're left with 2, arctan and sigma. Both are smooth, both stay between 0 and 1, and both preserve ordering. Honestly, either one could work. But one of them became the standard, not because it looks nicer, but because mathematicians like the shape. Because hidden inside this curve is a remarkable piece of mathematics. A piece of mathematics that makes probabilities, optimization, and machine learning fit together beautifully. So let's take a closer look, because this curve is the heart of logistic regression. So let's put everything together. Our robot sees a cell, a radius, a texture, smoothness, and dozens of other measurements. Each feature gets multiplied by its own weight. Some features matter more and some features matter less. Add everything together and we get a score Z. A large score means the cell looks suspicious. A large negative score means the cell looks harmless. But a score isn't a probability. So we pass it through the sigmoid, and suddenly out comes something we can actually interpret. 0.02, 2% chance of being malignant. 0.95, 95% chance of being malignant. So the full model looks like this. Y hat is equal to sigma z, where z is equal to x theta. And that's logistic regression. A score transformed into a probability. Simple, elegant, and surprisingly beautiful. But there's still a mystery. Those weights, the theta vector we're talking about, where did they come from? How did the model decide which features matter? How does it learn? To answer that, we need to talk about the cost function. So we have our equation, but we still need to find the weight, the theta vector. And to find the weight, we need to measure how wrong we are. You might already have an idea. We use the mean square error for linear regression. We take the difference between the prediction and reality, square it, and average it. So why not use it here? Let's try. Suppose our model predicts 0.99. Almost certain this cell is malignant, but the true label is 0, the 9. That is a catastrophically wrong prediction. The model was confident and completely wrong. MSE gives us 0.99 minus 0 squared, which is 0.98, just under 1. Now, suppose for the same cell, the model predicts 0.6, slightly leaning towards malignant. Also wrong, but far less confident. MSE gives us 0.6 minus 0 squared, which is 0.36. So the catastrophically confident wrong prediction is only penalized about twice as much as the uncertain one. That doesn't feel right. Being confidently wrong should hurt a lot more. But there's a deeper problem. When you take the derivative of the MSE through a sigmoid, the surface loses its clean slope. Hills, valleys, flat regions, multiple places the model could get stuck. Gradient descent can't reliably find the problem. It settles here, here, or here. We need a loss function that looks like this instead, a clean convex bowl, just one valley, one bottom. And so that gradient descent always finds it. So we need a cost function that does two things. We need a cost function that punishes confident wrong predictions harshly and gives a convex loss surface to optimize. And if you're still confused, don't worry, we'll go to gradient descent in future videos. But the point is that MSE does neither. So what does? That's exactly what episode 3 is about. And I'd argue it's the most elegant part of the story, because the answer doesn't come from statistics, it comes from probability theory. And when you see how it all connects, it's one of those moments where machine learning suddenly makes sense. Like and subscribe to stay tuned for the next video.